Every so often a year comes along that feels quietly different, as though the universe itself has decided to reveal a few more of its secrets. 2025 has been one of those years. Not because everything changed overnight, but because, almost without announcement, several long-standing questions in astronomy began to find their answers, and, in doing so, posed entirely new ones. We have welcomed a third confirmed visitor from another star system. We have discovered a black hole lurking in a cluster we thought we understood completely. We have quietly realized that the Sun, our own star, is moving through the galaxy far faster than we had measured for decades. And, perhaps most tantalizing of all, we have found a small temperate world orbiting a quiet red dwarf just 18 light-years away, a planet that, until this year, had somehow escaped serious attention. What makes these moments special is not simply the discoveries themselves, but the way they were made, often with instruments that have been watching the sky for years, sometimes simply by looking again at photographs taken long ago with fresh eyes and better questions. It is a gentle reminder that the universe is under no obligation to hurry. It reveals itself when it is ready and, occasionally, when we are ready to listen. Before we explore these stories together, I'd like to ask you something I often wonder myself. If we had to choose one, would we rather know, beyond doubt, that life once existed on Mars, or discover a living world orbiting another star close enough that one day we might almost reach out and touch it? Leave your thoughts below if you'd like. There's no wrong answer. And now, let us see what 2025 has shown us. In July of 2025, astronomers spotted something extraordinary. A comet appeared in our telescopes that wasn't from around here, not from the outer reaches of our solar system, not from the Kuiper Belt or the Oort cloud. This thing came from another stellar system entirely. They named it Comet 3 I Atlas, and it's only the third confirmed interstellar visitor we've ever detected. Let's put that in perspective. Imagine you live on a remote island. Ships pass by occasionally, but they're always from nearby islands. You know their designs, recognize their flags, understand where they're going. Then one day, a vessel appears on the horizon that's completely different. Strange construction, unfamiliar materials, heading on a trajectory that doesn't match any local route. That's essentially what an interstellar comet represents. It's a messenger from another cosmic neighborhood, carrying information about places we've never been. The first interstellar visitor we confirmed was Oumuamua back in 2017. That object caused a sensation because it looked nothing like our comets. It was elongated, tumbling, and didn't show any of the typical cometary activity like a tail or coma. Some scientists even speculated it might be artificial, though most experts disagreed. Then in 2019, we found Comet Borisov, which looked and acted much more like a traditional comet, complete with a beautiful tail. Now, in 2025, we have our third visitor, and it's teaching us things the other two couldn't. Here's what made this discovery so valuable for research. It's big. We're talking about an object up to 5.6 kilometers across, roughly 3.5 miles. That's about the length of 56 football fields laid end to end. For comparison, Oumuamua was maybe a few hundred meters long, and Borisov was probably just over a kilometer. Size matters in astronomy because bigger objects retain more of their original material. They haven't been worn down as much by cosmic erosion. They're like older library books that have been checked out less often, so the pages are still readable. The Hubble Space Telescope got some incredible observations, and what it found was fascinating. The comet has extremely high carbon dioxide content. Now, you might wonder why that matters. Carbon dioxide isn't exactly rare in space. but the amount and type tells us about the conditions where this object formed. Think of it like analyzing someone's accent. The specific way they pronounce certain words tells you not just what country they're from, but sometimes even what city or neighborhood. The chemical composition is its accent, and it's telling us about the stellar neighborhood where it was born. What really excited scientists was determining the comet's age. Based on its composition and surface characteristics, this visitor is ancient, formed roughly when our own solar system came into being. But it formed somewhere else, around a different star, under different conditions. For eons, it's been traveling through the vast, empty regions between suns, in places where nothing much happens. Then, by pure chance, its path happened to intersect with our little corner of the galaxy. The timing was perfect for another reason. 3. I-Atlas reached perihelion in late 2025. Perihelion is the point in an orbit where an object comes closest to the Sun. For an interstellar visitor, this is the money shot. As it approaches the Sun, it heats up. Frozen gases vaporize. Material that's been locked away since the dawn of planetary formation suddenly becomes visible. It's like watching a time capsule open itself. Scientists from multiple space agencies coordinated their observations. The Hubble Space Telescope, the James Webb Space Telescope, ground-based observatories in Chile and Hawaii, even amateur astronomers with backyard telescopes contributed data. This multi-spacecraft and multi-telescope observation campaign wasn't just about getting pretty pictures. Each instrument sees different things. Hubble is great at visible light and ultraviolet. Webb specializes in infrared. Ground-based telescopes can track position changes over time. By combining all this data, astronomers could build up a complete picture of the visitor's trajectory, composition, structure, and activity level. It's like having multiple witnesses describe the same event from different angles. Each one sees something the others missed, and together they give you the full story. One of the key achievements was refining the comet's trajectory with extreme precision. This matters because if you know exactly where it came from, you can work backward and figure out which stellar system it originated from. Think of it as cosmic detective work. You've got a bullet, and you need to figure out which gun fired it and where that gun was located. Except the bullet has been flying for an incomprehensible span of time, and space isn't empty. Gravity from every star and planet it passed near would have nudged its trajectory slightly. You need incredibly precise measurements to work backward through all those influences. Early analysis suggested the comet might have come from a stellar system about 50 light-years away. Now, 50 light-years is actually pretty close in cosmic terms. The Milky Way galaxy is about 100,000 light-years across, so this visitor came from our general neighborhood. But even at its speed of several tens of kilometers per second, the journey would have taken longer than human civilization has existed. Longer than our entire species has walked the Earth. This cosmic wanderer was already traveling through space when dinosaurs roamed our planet. The chemical analysis revealed something else intriguing. Besides the high carbon dioxide content, the comet showed traces of complex organic molecules. Now, before anyone gets excited, organic molecules don't mean life. In chemistry, organic just means carbon-based compounds. But some of the molecules detected were fairly complex, the kind that could be building blocks for life under the right conditions. This raises interesting questions about how common these ingredients are throughout the galaxy. If an interstellar comet formed eons ago in a completely different stellar environment, contains similar organic compounds to what we find locally, it suggests that the raw materials for life might be pretty standard across the cosmos. There's also a practical reason why finding and studying these visitors matters. Right now, we're limited to studying our own solar system in detail, and observing distant stellar systems only as points of light or, at best, fuzzy blobs. We can't yet send probes to other planetary systems. The nearest star is over 4 light-years away, and with our current technology, getting there would take thousands of years. But interstellar comets are samples from alien worlds that come to us. They're like cosmic care packages. Each one is a free sample from another neighborhood of the galaxy. The more of them we can find and study, the more we learn about the diversity of planetary systems across the Milky Way. Before 2025, scientists estimated that an interstellar object passes through the inner solar system about once a year. But we only started spotting them recently because our detection technology has improved. Oumuamua in 2017 was probably the first one we were capable of detecting. Borisov in 2019 confirmed these things are relatively common. And now our third discovery gives us a larger sample size. With 3 confirmed detections in 8 years, we're starting to get a sense of the population. Astronomers estimate there could be thousands of these objects passing through the outer solar system at any given time. We just can't see most of them because they're small and dark and far away. This discovery also validated the importance of rapid response networks in astronomy. When the comet was first spotted in July 2025, astronomers immediately recognized from its trajectory that it was likely extrasolar. Within hours, observation time was scheduled on major telescopes worldwide. Data was shared in real time. Researchers from dozens of countries collaborated instantly. This kind of quick coordination would have been impossible a decade or 2 ago. Now it's standard practice, and it allowed scientists to extract maximum value from a fleeting opportunity. Because that's the thing about interstellar visitors. They don't stick around. This one came in fast, swung around the sun, and headed back out into deep space. By early 2026, it will be too faint for even our best telescopes to observe. In a few decades, it'll be back in the vast emptiness between stars, and we'll never see it again. This was humanity's one shot to study this particular messenger from beyond our solar system. And thanks to the rapid response and international cooperation, we made the most of it. The discovery also sparked renewed discussion about potential missions to intercept future interstellar visitors. Several space agencies have proposed concepts for spacecraft that could be launched on short notice when a new extrasolar object is detected. These would be essentially emergency missions, designed to reach the visitor while it's still in our neighborhood and get close-up observations or even land on it. The engineering challenges are significant. You need a spacecraft that can be assembled and launched in weeks or months, not years. You need engines powerful enough to match velocity with an object traveling tens of kilometers per second. And you need instruments hardy enough to survive the harsh environment while gathering useful data. But the scientific payoff would be immense. Imagine if we'd been able to land a probe on this comet. We could have directly sampled its surface material, analyzed its internal structure, measured its composition with laboratory precision rather than telescopic observations. Every extrasolar object we've detected so far has taught us new things about chemistry and planetary formation beyond our own backyard. A dedicated mission to one of these visitors would be like going from reading about a foreign country in books to actually visiting it. The level of detail and understanding would jump exponentially. Looking forward, this discovery in 2025 will likely be remembered as the moment when interstellar objects moved from curiosities to legitimate targets of scientific inquiry. We now have enough data points to start making generalizations. We can begin to categorize these cosmic travelers. Some, like Oumuamua, are rocky and asteroid-like. Others, like Borisov and our latest find, are icy and comet-like. This suggests that other stellar systems have similar diversity to our own. They have rocky inner regions and icy outer regions. They have processes that occasionally kick objects out into the void, just like our solar system does. In fact, our own solar system probably contributes its fair share of interstellar wanderers. Gravitational interactions, particularly with Jupiter, occasionally fling comets and asteroids onto trajectories that send them out of our neighborhood entirely. These objects then become cosmic travelers, perhaps eventually passing through some alien planetary system in the distant future. Maybe somewhere out there, alien astronomers are observing one of our solar system's comets and puzzling over its composition, just like we're doing with our recent visitor. It's a humbling thought. We're not just observers of this cosmic exchange program, we're participants in it. In February of 2025, the James Webb Space Telescope spotted something no one had ever seen before: a new moon orbiting Uranus. They designated it S2025-U1, following the standard naming convention for newly discovered satellites. This little moon is only about 10 kilometers or 6 miles across, which in cosmic terms is tiny. But its discovery tells us a lot about both Uranus and the capabilities of our most advanced space telescopes. Uranus is one of the ice giants in our solar system, and it's always been a bit mysterious. It's so far from Earth, over 2.8 billion kilometers or 1.7 billion miles at its closest approach, that detailed observations are challenging. We've only visited it once, briefly, when Voyager 2 flew past in 1986. That flyby gave us our only close-up look at the Uranian system. Voyager 2 discovered 10 new moons during its encounter, bringing the total to 15 at the time. Since then, ground-based and space-based telescopes have found more, and with this latest discovery, Uranus now has 29 known moons. You might wonder why Voyager 2 missed this particular moon during its flyby. The answer is simple. It's incredibly faint. Think about trying to photograph a small, dark rock in a dimly lit room from far away. Even with a good camera, you might not see it, especially if you're moving quickly and can't take long exposures. That's essentially what happened in 1986. Voyager 2 was traveling past Uranus at about 15 kilometers or 9 miles per second. It had limited time for observations, and its cameras, while excellent for their era, couldn't detect very faint objects. S2025-U1 would have been far too dim to show up in Voyager's images. But the James Webb Space Telescope is a different beast entirely. Webb orbits the Sun at a point called L2, which is about 1.5 million kilometers or almost 1 million miles from Earth, on the opposite side from the Sunday. From this stable position, it can stare at distant objects for hours or even days, gathering every photon of light. Its massive mirror, 6.5 meters or over 21 feet across, collects far more light than Voyager's cameras could. And its infrared detectors are sensitive to wavelengths of light that reveal faint, cold objects that might be invisible light. When Webb turned its attention to Uranus in February 2025, astronomers were actually looking for something else. They were studying Uranus's ring system, trying to understand its structure and composition. The rings of Uranus are much fainter than Saturn's famous rings, and they're tilted at an odd angle because Uranus itself is tilted on its side. As Webb's instruments scanned the region around the planet, they picked up a faint point of light that didn't match any previously known moon. This is actually how many astronomical discoveries happen. You're looking for one thing and stumble across something else entirely. Follow-up observations confirmed it was indeed a moon. By tracking its position over several weeks astronomers could determine its orbit. S2025. One orbits Uranus in the same general region as several other irregular moons. Irregular moons are different from regular moons. Regular moons, like our own moon, orbit in nearly circular paths aligned with their planet's equator. They probably formed from the same disk of material as the planet itself. Irregular moons have tilted, often elliptical orbits. They move in various directions, sometimes even backwards compared to the planet's rotation. Scientists think these are captured objects. They formed elsewhere and were later grabbed by the planet's gravity. The discovery of S2025 helps astronomers understand how this capture process works. Uranus's irregular moons cluster into several groups based on their orbital characteristics. Each group probably represents the fragments of a larger object that got captured and then broke apart, either from a collision or because tidal forces tore it apart. By studying the orbits of all these irregular moons, including the newly discovered one, scientists can work backward and figure out the history of captures and collisions. It's like being a detective at a crime scene, except the crime happened millions or billions of years ago, and all you have are these small pieces of evidence floating in orbit. There's also a connection between Uranus's moons and its ring system. Uranus has 13 known rings, most of which are quite narrow and faint. Scientists believe these rings might be sustained by small moons acting as shepherd satellites. Imagine two sheepdogs keeping a flock together, one on each side. The gravitational influence of these shepherd moons keeps ring particles confined to narrow bands. Saturn's rings have several confirmed shepherd moons. Uranus probably works the same way, but many of these shepherd moons might be too small and faint to detect easily. S2025 might be one of them, or it might help us understand the orbital dynamics that govern the whole system. The composition of this new moon is still unknown. At 10 kilometers or 6 miles across, it's too small for Webb to determine what it's made of directly. But based on the other irregular moons of Uranus, it's probably a mix of rock and ice covered in a dark, carbon-rich material that makes it reflect very little light. This dark coating is common on objects in the outer solar system. It's probably organic material that's been altered by radiation over billions of years, turning into a dark reddish-brown substance. If you could stand on the surface of S2025 you'd be standing on a small, dark, cratered world where the sun appears as just a bright star and Uranus dominates the sky as a pale blue-green disk. The discovery also showcases an important capability of the James Webb Space Telescope that often gets overshadowed by its more glamorous missions to observe distant galaxies. Webb is fantastic at studying objects in our own solar system. Its infrared vision can see through dust and can detect the heat signatures of cold objects. Its sensitivity means it can spot things too faint for other telescopes, and its precision pointing allows it to track moving objects as they orbit the Sun. Since its launch, Webb has observed Mars, Jupiter, Saturn, Uranus, Neptune, asteroids, comets, and various moons. Each observation has yielded new discoveries or refined our understanding of these familiar yet still mysterious worlds. For Uranus specifically, 2025 was a particularly important year of observations. There's increasing interest in sending a dedicated mission to Uranus. The last time we visited was 39 years ago with Voyager 2. A modern orbiter mission could revolutionize our understanding of ice giant planets, which represent a whole category of world that we've barely explored. More than half of the exoplanets we've discovered are similar in size to Uranus and Neptune. They're probably ice giants too. But we can't understand those distant worlds without first understanding the ice giants in our own backyard. A future Uranus orbiter mission would need to know about all the moons to plan its trajectory and observation strategy. The discovery of S2025U1 might seem like just adding one more name to a list, but each moon is a potential scientific target. Each one has a story to tell about the formation and evolution of the Uranian system. And finding these small moons now, while mission planners are still designing potential spacecraft, ensures they can be included in the mission concept. It would be frustrating to arrive at Uranus and then discover a moon you didn't know about, realizing you could have planned to study it if you'd known it was there. There's also scientific value in simply knowing how many moons a planet has. It tells us about the planet's capture history, its gravitational influence, and the population of small bodies in that region of the solar system. Jupiter has 95 known moons. Saturn has 146. Uranus now has 29, and Neptune has 16. But these numbers are incomplete. We've probably only found the larger moons. There are likely hundreds or thousands of smaller moons orbiting these giant planets, too small and faint for us to detect with current technology. Each new discovery gives us a slightly better census of what's actually out there. The naming of this moon is also interesting. Right now it's designated S2025U1, which is a temporary designation. The S stands for satellite. 2025 is the year of discovery. U stands for Uranus. And 1 means it was the first new Uranian moon discovered that year. Eventually, if the orbit is confirmed and the moon is studied further, it will receive a permanent name. For Uranus, the convention is to name moons after characters from the works of William Shakespeare and Alexander Pope. So this little moon might eventually be called something like Ariel or Puck or Titania, except those names are already taken. It'll need to be a character that hasn't been used yet, probably from a lesser-known play or poem. Looking at the bigger picture, the discovery of S2025U1 represents a milestone in our exploration of the outer solar system. For decades, we've been finding new moons around Jupiter and Saturn because they're closer and easier to study. Discoveries around Uranus and Neptune are rarer. Each one requires cutting-edge technology and careful observation. The fact that Webb could spot this faint moon on what was essentially a routine observation of Uranus's rings shows just how powerful modern space telescopes have become. We're now able to study the outer solar system with a level of detail that was unimaginable even a decade ago. This discovery also reminds us that our solar system is still a place of exploration and discovery. We often think of space exploration as being about distant galaxies or searching for Earth-like exoplanets. But there's still so much we don't know about our own cosmic neighborhood. Every planet has secrets. Every moon has a story. And even after centuries of telescopic observations and decades of space missions, we're still finding new things in our own backyard. S2025U1 might be small and faint and far away, but its discovery tells us we haven't finished exploring our solar system. We're still making first contacts with worlds no human eyes have ever seen before. In September of 2025, NASA made an announcement that sent ripples through the scientific community and captured headlines worldwide. Researchers studying a rock called Chiava Falls, collected by the Perseverance rover, had ruled out all the non-biological explanations they could think of for its unusual features. This doesn't prove the rock contains evidence of ancient Martian life, but it means the possibility is now much stronger than before. To understand why this matters, we need to back up and explain what Perseverance found and why it's significant. The rover has been exploring Jezero crater since February of 2021. Jezero was chosen because it was once a lake billions of years ago. Water flowed into it through river channels, depositing sediment and minerals. If life ever existed on Mars, a place like Jezero would be a prime location. Wherever you find water on Earth, you find life. The logic is that the same might be true on Mars, or at least it might have been true when Mars was warmer and wetter billions of years ago. Perseverance collected the Shayava Falls rock in 2024 from a region of Jezero that showed signs of ancient water activity. The rock itself is a fine-grained sedimentary rock, the kind that forms when tiny particles settle out of water. Think of it like mud at the bottom of a lake that eventually turns into solid rock over millions of years. But what caught scientists' attention were unusual spots on the rock's surface. These spots, which they nicknamed leopard spots because of their appearance, contain organic compounds surrounded by crystals that typically form in the presence of water. Now, organic compounds by themselves aren't evidence of life. Organic just means carbon-based, and carbon is common throughout the universe. Meteorites contain organic compounds. Comets contain them. You can make organic compounds through purely chemical processes without any biology involved. But the specific pattern in Shayava Falls was intriguing. The organic compounds were concentrated in these spots, and the spots were surrounded by a white rim of minerals that usually form when water interacts with rock. The whole arrangement looked similar to some patterns on Earth that are created by microbes. The initial analysis in 2024 was cautious. Scientists found the rock interesting, but pointed out several ways these features could have formed without life. Maybe the organic compounds came from Martian meteorites that fell on the surface. Maybe chemical reactions in the rock created the pattern without any biology. Maybe it was some geological process we don't fully understand yet. Science requires ruling out all the conventional explanations before you start considering extraordinary ones. And ancient life on Mars would be pretty extraordinary. That's what made the September 2025 announcement significant. Researchers had spent over a year trying to explain Shayava Falls through non-biological processes. They ran experiments. They created models. They consulted with geologists, chemists, and microbiologists. And one by one, the non-biological explanations started to fail. The organic compounds had a signature that didn't match typical Martian meteorites. The mineral patterns couldn't be easily explained by known chemical reactions. The arrangement of features seemed too organized to be random. To put this in perspective, imagine finding footprints in the forest. At first, you think maybe it's just an interesting pattern in the mud. You consider whether water erosion could have made that shape. Maybe falling leaves created the impression. You rule out one possibility after another. And as you eliminate each alternative explanation, the likelihood that these really are footprints from an animal increases. That's essentially where we are with Shayava Falls. We can't yet say for certain these features were made by ancient Martian microbes, but we're running out of other good explanations. The rock shows what geologists call biosignatures. These are features that could potentially have been created by life. On Earth, certain mineral deposits, certain chemical signatures, certain physical structures are known to be produced by microorganisms. When you find similar features in ancient Earth rocks, especially multiple different biosignatures together, it's strong evidence for ancient life. Shayava Falls has several of these features together. The organic compounds, the mineral rinds, the specific pattern of the spots. The combination is what makes it compelling. But here's the challenge. We can't study Shayava Falls in detail because it's still on Mars. Perseverance has excellent instruments for a rover, but they're limited compared to what we can do in Earth-based laboratories. The rover can take close-up images. It can analyze chemical composition using lasers and spectrometers. It can even study the rock's internal structure using radar. But it can't slice the rock into thin sections and examine it under an electron microscope. It can't extract and sequence any potential organic molecules. It can't perform all the tests that would definitively determine whether these features are biological or not. That's why there's so much emphasis on the Mars Sample Return mission. Perseverance isn't just studying rocks. It's collecting samples and storing them in sealed tubes. The plan is for a future mission to pick up these tubes and bring them back to Earth, where they can be studied in detail by laboratories around the world. Chayava Falls is one of the samples already collected. When it eventually arrives on Earth, possibly in the early 2030s, if the mission stays on schedule, it will be subjected to an incredible battery of tests. Scientists from multiple disciplines will examine every aspect of this rock. Only then will we know for certain whether it contains evidence of ancient life. The September 2025 findings reinvigorated the Mars Sample Return mission and gave it new urgency. Before this announcement, some people questioned whether returning samples was worth the expense and complexity. After all, Perseverance and other rovers can do a lot of science on their own. But Chayava Falls demonstrates the limitation of remote analysis. There are questions you simply can't answer without getting samples into sophisticated Earth-based laboratories. This rock might be the key to one of humanity's biggest questions. Are we alone in the universe? And to answer that question, we need to bring it home. The implications of finding ancient life on Mars would be profound. It would mean life arose independently at least twice in our solar system. That would suggest life is probably common throughout the universe. Every star would be a potential sun for living worlds. Every planet in the habitable zone would be a place where biology might emerge. The universe would transform from a vast, empty, sterile place into a garden teeming with life at various stages of development. That's a massive shift in perspective. But even if the Chayava Falls features turn out to be non-biological after all, the rock is still valuable. It represents ancient Martian conditions. It tells us about the chemistry and geology of early Mars. It provides clues about how the planet evolved from a warmer, wetter world to the cold, dry desert it is today. Every rock Perseverance studies adds to our understanding of planetary evolution, which helps us understand not just Mars, but Earth and other rocky planets throughout the galaxy. There's also something poetic about the fact that this discovery came from Jezero Crater. Jezero means lake in several Slavic languages. The crater was named decades ago based on its resemblance to a dried lake bed. Now we're finding potential evidence of ancient life in sediments that settled at the bottom of that lake billions of years ago. If confirmed, this would mean we found evidence of life in one of the most obvious places to look. It's like searching for historical artifacts and finding them in the ruins of an ancient city near a riverbank. Life goes where the water is. The timing of this discovery in 2025 also comes at an interesting moment for Mars exploration. Multiple missions are planned for the coming decade. China is developing a sample return mission. NASA and ESA are working on their sample return mission. Private companies are talking about eventual crewed missions to Mars. The more we learn about ancient Martian conditions, including the possibility of past life, the more context we have for these future missions. Understanding Mars's biological potential isn't just about satisfying scientific curiosity. It's about preparing for the day when humans might become a multiplanetary species. One thing the Chayava Falls findings emphasized is the importance of choosing the right landing sites for Mars missions. Perseverance went to Jezero specifically because it showed signs of ancient water activity. That choice is now paying off. Future missions will need similar, careful site selection. We've only explored tiny fractions of Mars's surface with rovers. There are countless other ancient lakebeds, river deltas and hydrothermal areas that might preserve evidence of past life. Each mission can only visit one location, so choosing wisely is crucial. The September 2025 announcement also sparked renewed discussion about what counts as proof of life. This is a surprisingly tricky question. On Earth, we can often bring living organisms into the lab and study them directly. But for ancient life, we're looking at fossils and chemical signatures. For potential life on Mars, we're looking at rocks that are billions of years old, analyzing them from millions of kilometers or miles away, or, eventually, in laboratories that need to avoid contaminating the samples with Earth life. The standards of proof need to be incredibly high. One ambiguous rock isn't enough. We need multiple lines of evidence, ideally from multiple locations, all pointing to the same conclusion. That's why scientists are being careful not to declare victory prematurely with Chayava Falls. The rock is promising, very promising. But it's one data point. Science requires repeatability. We need to find similar features in other Martian rocks. We need to study this rock in Earth laboratories. We need to eliminate every possible non-biological explanation until life is the only reasonable conclusion left. That process takes time, and it requires patience. But that's how good science works. You don't rush to conclusions. You follow the evidence wherever it leads, and you change your mind only when the evidence demands it. Looking forward, the Chayava Falls discovery will likely be remembered as a turning point, regardless of how it ultimately turns out. If confirmed as biological, it's one of the most important discoveries in human history. If it turns out to be non-biological, it's still a valuable lesson in Martian geology and a reminder that we need to bring samples back for detailed study. Either way, it represents 2025 as a year when the search for life beyond Earth moved from speculation to serious scientific investigation based on concrete evidence. That's a milestone worth marking. In March of 2025, astronomers announced a discovery that sounds like pure science fiction. A supermassive black hole, roughly 600,000 times the mass of our Sun, was found hiding at the center of the Large Magellanic Cloud. And this black hole wasn't doing any of the dramatic things that usually give black holes away. It wasn't actively feeding. It wasn't blasting out jets of radiation. It was completely silent, surrounded only by a swarm of stars racing away at unbelievable speeds. The only reason we found it at all was because of those stars and the way they were moving. The Large Magellanic Cloud, LMC, is a small, irregular galaxy that orbits our Milky Way. From the southern hemisphere, you can see it with the naked eye as a faint, fuzzy patch in the constellations Dorado and Mensa. At about 160,000 light-years away, it's the closest full-fledged galaxy to us. Because it's relatively nearby, we can study individual stars inside it in exquisite detail, and that's exactly what the European Space Agency's Gaia mission has been doing for more than a decade. Gaia is a space telescope with one overriding purpose: to measure the positions, distances, and motions of stars with unprecedented precision. Since its launch in 2013, it has mapped well over 2 billion stars, creating what astronomers call an astrometric catalogue, a dynamic, three-dimensional movie of our galaxy and its neighbors. Most stars move at sedate, predictable speeds, following the gentle rotation of their host galaxy. Every once in a while, though, Gaia spots something moving far too fast for its surroundings. These are hypervelocity stars, and they are exceedingly rare. A star becomes hypervelocity when it has a close gravitational encounter with something extremely massive and compact. Picture a game of crack the whip on ice. The skaters on the end of the line get flung outward at terrifying speed, while the center barely budges. Black holes, especially supermassive ones, can play the same trick on stars. If a star, or a binary pair, swings too close, the black hole's gravity can catapult one or both components to speeds of hundreds or even thousands of kilometers per second, sometimes fast enough to escape the galaxy forever. In early 2025, a research team poring over the latest Gaia data noticed something bizarre in the Large Magellanic Cloud. Dozens of stars were moving at hypervelocity speeds over 1,000,000 miles per hour, but they weren't all fleeing in random directions, as you'd expect from isolated slingshot events. Instead, when the researchers traced their trajectories backward in time, every single path converged on the same invisible point near the galaxy's center. It looked exactly like a group of pinballs scattering away from a single bumper hidden in the middle of the table. Something enormous was sitting there, flinging stars in every direction. Other telescopes were immediately pointed at that spot. The verdict? Nothing to see. No bright quasar-like glow, no accretion disk, no X-ray emission or radio jets. Just empty space. Yet the orbital mechanics were unambiguous. To accelerate stars to those velocities required a mass of several 100,000 suns crammed into a region smaller than our solar system. The only object in the universe that matches that description is a dormant, supermassive black hole, one that has run out of gas to eat and has gone dark. This discovery is groundbreaking for several reasons. First, it proves that quiet, supermassive black holes are out there and can be found purely through their gravitational influence. Almost every supermassive black hole we've discovered until now announced itself by gorging on infalling material and shining brighter than 1,000,000,000,000 suns. This one is the opposite, a cosmic dragon that has fallen asleep because its pantry is empty. Finding it shows that the universe is full of these sleeping giants, and most of them will stay invisible unless we look for the gravitational ripples they leave behind. Second, it gives us a priceless new laboratory for studying galaxy evolution. The Large Magellanic Cloud has roughly 1/4 the heavy element content, metallicity, of the Milky Way. Stars born in low metallicity gas behave differently. They lose less mass through stellar winds and can collapse more completely when they die. The mere existence of a 26000000 M black hole in such an environment helps refine our models of how supermassive seeds grow in the early universe, especially in the metal-poor conditions that dominated billions of years ago. Third, it reminds us how much of the ordinary baryonic matter in the universe is dark. We usually think of dark matter as some exotic, unknown particle, but a huge fraction of normal matter is also invisible. Stellar remnants, rogue planets, and above all, quiet black holes. This discovery is a proof of concept that astrometry alone can map that hidden mass. There's a delightful detective story behind the find, too. Gaia has been collecting data since 2013, but the real breakthrough came from improved machine learning algorithms trained to flag unusual proper motion patterns. The computers noticed the converging hypervelocity stars. Humans did the follow-up and realized what they were looking at. This blend of big data and clever code is now the standard way major discoveries are made. Looking ahead, the LMC black hole is only the beginning. The Milky Way is currently devouring the Large Magellanic Cloud. In a couple of billion years, its stars and its silent central black hole will become part of our own galaxy. Every dwarf galaxy the Milky Way has swallowed in the past likely delivered its own dormant, supermassive black hole. Over cosmic time, these quiet mergers are how today's giant galaxies assembled their central monsters. Perhaps most exciting of all, Gaia's catalogue keeps getting better. Each new data release improves the precision, letting us detect ever subtler gravitational tugs. In the coming years, we will almost certainly find more of these invisible giants, not by their light, but by the way they make the stars around them dance. In the context of 2025's banner year of discoveries, the silent supermassive black hole in the Large Magellanic Cloud stands out as a perfect symbol of how much of the universe remains hidden in plain sight. We naturally focus on objects that blaze with light, but the cosmos is also full of shadows that only reveal themselves when we watch carefully enough, patiently enough, and cleverly enough. This 600,000 solar mass ghost, betrayed only by the terrified flight of the stars it once flung away, is a reminder that the age of black hole astronomy has entered a completely new phase 1, where darkness itself becomes the clue. In October of 2025, astronomers announced the discovery of a rocky planet that immediately jumped to the top of the list of potentially habitable worlds. They designated it GJ251c, and it's located 18.2 light-years from Earth. That might sound like a huge distance, and it is by everyday standards. Light takes over 18 years to travel from that star to us. But in galactic terms, 18 light-years is practically next door. There are hundreds of billions of stars in the Milky Way, and this is one of the closest ones that has a planet in the habitable zone. GJ251 is a red dwarf star, much smaller and cooler than our Sun. Red dwarfs are the most common type of star in the galaxy, making up about 70% of all stars. They're long-lived, burning their fuel slowly and steadily for trillions of years. Our Sun will eventually puff up into a red giant and then fade to a white dwarf in about 5 billion years. Red dwarfs can shine for 10 trillion years or more. They're the marathon runners of the stellar world, while stars like our Sun are sprinters by comparison. Because red dwarfs are cooler than Sun-like stars, their habitable zone sits much closer to the star. The habitable zone is the region where a planet receives just the right amount of starlight to maintain liquid water on its surface. Too close, and water boils away. Too far, and it freezes solid. For our Sun, Earth sits comfortably in the habitable zone. Venus is too close, Mars is too far, though Mars was probably habitable billions of years ago when it was warmer. For a red dwarf, like GJ251, the habitable zone is much closer because the star is much dimmer. GJ251c orbits its star every 54 days. Think about that. Its year is less than 2 Earth months long. It's so close to its star that it's probably tidally locked, meaning one side always faces the star while the other side is in permanent darkness, just like how our moon always shows the same face to Earth. This creates some interesting climate dynamics. The day side would be hot, constantly bathed in starlight. The night side would be freezing. But in between, in the twilight zone where day and night meet, conditions might be just right for liquid water to exist. The planet itself is classified as a super-Earth, which is a somewhat misleading term. It doesn't mean it's exactly like Earth, but bigger. It just means it's a rocky planet more massive than Earth, but not massive enough to be a gas giant like Neptune. GJ251c has about 4 times Earth's mass. This probably means it's larger than Earth and has stronger surface gravity. If you could stand on its surface, you'd weigh about 100 to 120% more than you do on Earth. That's enough to feel noticeably heavier, like carrying a heavy backpack, but not impossible to adapt to. The discovery came from a combination of ground-based observations and space telescope data. The planet was initially detected using the radial velocity method. This technique measures how a star wobbles as its planets orbit around it. Planets don't actually orbit around the center of their star. Both the planet and star orbit around their common center of mass, called the barycenter. For our solar system, the Sun wobbles slightly because Jupiter is so massive. This wobble is tiny but measurable. As the star moves toward us, its light shifts slightly toward the blue end of the spectrum. As it moves away, the light shifts toward red. By measuring these tiny shifts repeatedly over time, astronomers can detect planets and determine their mass and orbital period. GJ251c showed up as a periodic wobble in its star's motion with a 54-day pattern. Follow-up observations using different telescopes confirmed the signal. Then space-based observations helped characterize the planet further. By combining multiple detection methods and observation techniques, astronomers built up a detailed picture of this distant world. What makes GJ251c particularly exciting is its potential for atmospheric studies. At 18.2 light-years away, it's close enough that future telescopes might be able to analyze its atmosphere if it has one. When a planet passes in front of its star from our perspective, an event called a transit, starlight filters through the planet's atmosphere. Different molecules in the atmosphere absorb different wavelengths of light, creating a unique signature that we can detect with sensitive instruments. This technique has been used to study the atmospheres of hot Jupiter planets, which are easy targets because they're large and have thick atmospheres. But rocky planets are much harder because they're smaller and their atmospheres are thinner. The James Webb Space Telescope and future next-generation telescopes being designed now might be able to study GJ251c's atmosphere if it transits from our point of view. The chances depend on the planet's orbital inclination. If the orbit is tilted just right, we'll see transits. If it's tilted too much, the planet will pass above or below the star from our perspective, and we won't see transits. Ground-based observations in late 2025 suggested the orbit might be favorable, but it will take more observations to be sure. If we can study the atmosphere, we'll look for biosignatures, which are signs that life might be present. On Earth, oxygen is a biosignature. Our atmosphere contains 20% oxygen, and almost all of that comes from photosynthesis by plants and microorganisms. Without life constantly replenishing it, oxygen would react with rocks and other chemicals and disappear from the atmosphere within a few million years. So, if we found oxygen in the atmosphere of an exoplanet, especially combined with other gases like methane that don't naturally coexist in stable equilibrium, it would suggest something is producing those gases, that something could be life. Of course, we need to be careful about jumping to conclusions. There are non-biological ways to produce oxygen and other gases. Ultraviolet light from the star can split water molecules into hydrogen and oxygen. Volcanic activity can release various gases. Chemical reactions in the atmosphere can create complex mixtures, but the combination and proportions matter. Life produces specific patterns of gases that are hard to explain through non-biological processes alone. If we found those patterns on GJ251c, it would be incredibly strong evidence for extraterrestrial life. Even if the planet turns out to be uninhabited, studying it would still be valuable. Every exoplanet we can characterize in detail adds to our understanding of planetary diversity. We found thousands of exoplanets, but for most of them, we know only basic facts like their mass and orbital period. Detailed atmospheric studies are rare and precious. Each one teaches us something new about how planets form, how atmospheres evolve, and what factors make a planet habitable or inhospitable. Red dwarf planets like GJ251c are particularly interesting because they're so common. If we want to find life elsewhere in the galaxy, red dwarfs are where we should look just by statistics. There are so many of them, and many have rocky planets in their habitable zones. But red dwarfs also present challenges for life. They're prone to flares, sudden brightening events where the star's output can increase dramatically for minutes or hours. These flares release intense radiation, including ultraviolet and X-rays, that could sterilize a planet's surface. A planet orbiting a red dwarf would need a strong magnetic field to deflect this radiation, or a thick atmosphere to absorb it, or perhaps life might exist underground or in oceans where it's shielded from the surface radiation. The discovery of GJ251c in 2025 adds another nearby target to our growing list of potentially habitable worlds. Other nearby examples include Proxima Centauri b, the closest known exoplanet at just 4.2 light-years away, and the TRAPPIST-1 system, which has 7 rocky planets, 3 of which orbit in the habitable zone. Each of these systems is close enough that we might eventually send probes there, not with current technology, but perhaps within a few generations if we develop faster propulsion systems. There's something deeply compelling about finding potentially habitable worlds so close to home. It makes the universe feel less empty. It suggests that wherever we look, if we look carefully enough, we'll find places where life might exist or could exist. The universe is vast beyond comprehension, but it's also full of interesting places. And some of those places are close enough that we might actually visit them someday, not just with robots, but with humans. Imagine a future where we have telescopes powerful enough to actually image planets like GJ251c directly, not just detect them as wobbles in starlight or dips in brightness during transits, but actually see them as dots, or even resolve surface features. We're not there yet with current technology, but future space telescopes using techniques like star shades or interferometry might achieve it. We could watch weather patterns on these distant worlds. We could map their continents and oceans, if they have them. We could search for lights on the night side that might indicate technological civilization. The planets we're discovering now are setting the targets for decades of future observations and missions. In the context of 2025, GJ251c represents hope and possibility. Every year, we find more exoplanets. Every year, some of them are in habitable zones. But GJ251c is special because of its proximity, its size, and its potential for follow-up studies. It's not just another name in a catalogue. It's a world we might actually be able to study in detail and understand as a place rather than just a data point. And if we're incredibly lucky, it might be a place where life exists, proving once and for all that we're not alone in the universe. 2025 brought us a discovery that challenges everything we thought we knew about how black holes form. The James Webb Space Telescope confirmed an actively feeding supermassive black hole in a galaxy that existed just 570 million years after the Big Bang. To give you a sense of how mind-boggling that is, the universe is about 13.8 billion years old. This galaxy existed when the universe was only about 4% of its current age. It's like finding a fully grown tree in a field that was bare dirt just a few months ago. The galaxy itself, designated CANU CSLRDZ 8.6, is what astronomers call a mystery galaxy. These are extremely faint, distant objects that Webb has been spotting in deep field images. They're mysterious because they shouldn't exist, or at least they shouldn't exist in the form we're seeing them. Standard theories of galaxy and black hole formation predict a gradual process. First, small clouds of gas collapse under their own gravity. These form the first stars. The stars live, die, and explode as supernovae. Some collapse into black holes. These black holes gradually merge and grow over hundreds of millions of years, eventually forming the supermassive black holes we see at the centers of galaxies today. But CANUCSLRDZ 8.6 has a supermassive black hole millions of times the mass of the Sun, and it's already there when the universe is barely 500 million years old. That's not enough time for the gradual process to work. It's like baking a cake and finding it fully frosted before you've even mixed the ingredients. Something doesn't add up, and that's what makes this discovery so important. When observations contradict theory, either the observations are wrong or the theory is wrong. In this case, the observations have been checked and double-checked. Webb's instruments are incredibly reliable, so the theory probably needs revision. Let's talk about what a supermassive black hole actually is. These are black holes millions or billions of times the mass of the Sun. Every large galaxy seems to have one at its center. The Milky Way has one called Sagittarius A star, weighing in at about 4 million solar masses. Larger galaxies have larger central black holes. The biggest ones we've found are tens of billions of solar masses, which is an almost incomprehensible amount of matter compressed into a region smaller than our solar system. Supermassive black holes are interesting because they're too big to form from a single star collapsing. The biggest stars we know of are maybe a few hundred times the Sun's mass. When they die, they can form black holes. But these stellar mass black holes are typically 10 to 100 solar masses, not millions. To build a supermassive black hole, you need to merge many smaller black holes together or have the black hole gradually accrete matter over time. Both processes are slow. Mergers take time because black holes need to find each other and spiral together. Accretion is limited by how fast material can fall in, which depends on things like radiation pressure from the hot accretion disk pushing material away. Current models suggested it would take at least several 100 million years, maybe 1 billion years, to grow a supermassive black hole from scratch. So finding one at 570 million years post-Big Bang means either it formed incredibly fast or it started from something already massive. Neither option fits neatly with our previous understanding. One possibility is direct collapse. Maybe in the early universe, conditions were different enough that massive black holes could form directly from collapsing gas clouds without going through the star stage. Think of it like water freezing. Usually, water freezes from tiny ice crystals that gradually grow. But if you supercool water carefully, it can suddenly freeze all at once into a solid block. Perhaps in the early universe, under specific conditions, clouds of gas could collapse directly into black holes without fragmenting into stars first. This would create seed black holes that are already thousands or even millions of solar masses, giving them a head start on growth. Another possibility is that black hole mergers happened much more frequently in the early universe than we thought. Galaxies were smaller and closer together back then. The universe was denser. Maybe black holes found each other and merged more easily. If you had hundreds or thousands of smaller black holes merging in quick succession, you could build up a supermassive black hole relatively quickly. It's like compound interest. Each merger makes the black hole bigger, which makes it easier to capture more material and merge with more black holes, accelerating the growth. The galaxy itself is tiny by modern standards. It's a fraction of the size of the Milky Way. But the black hole at its center is huge relative to the galaxy's size. In modern galaxies, the central black hole typically contains about 0.1% of the galaxy's total mass. It's a significant component, but not dominant. In CANUCSLRDZ 8.6, the black hole might contain a much larger fraction of the total mass. It's like a small town with an enormous factory at its center. The proportions are all wrong by modern standards, but maybe that's normal for the early universe. This discovery connects to another puzzle about the early universe. Webb has been finding mature galaxies existing earlier than we expected. Large spiral galaxies, structured disks, organized star populations, all appearing when the universe was supposedly still in its chaotic youth. It's like finding a well-organized library in a newly constructed building. You expect to find boxes everywhere, construction materials, things half finished. Instead, everything is neat and catalogued. It suggests the early universe was more organized than we thought, or structures formed faster than current models predict. One fascinating aspect of studying these early black holes is what they tell us about cosmic dawn. That's the period when the first stars and galaxies formed, lighting up the universe for the first time. Before cosmic dawn, the universe was dark. Hydrogen atoms filled space, but they were neutral and didn't emit light. As the first stars turned on, their radiation ionized the hydrogen, transforming it from neutral atoms into charged particles that interact with light differently. This period, called reionization, fundamentally changed the universe's appearance. Supermassive black holes contribute to reionization. When they actively feed, they emit enormous amounts of radiation. This radiation can ionize hydrogen across vast distances, creating bubbles of ionized gas expanding around each active black hole. Finding a big black hole so early means it was contributing to reionization earlier than we thought. It was one of the universe's first lighthouses, illuminating the darkness and transforming the space around it. The detection itself is impressive. CANUCSLRDZ 8.6 is incredibly faint and incredibly distant. To spot it, Webb used its deepest, most sensitive observing mode, staring at a tiny patch of sky for dozens of hours. The light from this galaxy has been traveling for over 13 billion years to reach us. When that light left the galaxy, the universe was less than 600 million years old. Earth didn't exist. The Sun didn't exist. The Milky Way as we know it didn't exist. We're literally looking back to a time before our cosmic neighborhood formed. The light itself is stretched by the expansion of the universe. This is called redshift. As the universe expands, the wavelengths of light get stretched longer, shifting toward the red end of the spectrum. For very distant objects, this shift is extreme. Light that was emitted in the ultraviolet gets stretched all the way into the infrared by the time it reaches us. That's why Webb is so crucial for these discoveries. It specializes in infrared observation, allowing it to see these extremely redshifted distant objects that are invisible to optical telescopes. The black hole in CANUCSLRDZ 8.6 isn't just sitting quietly, it's actively accreting, pulling in material from its surroundings. We can tell because it's emitting characteristic radiation patterns. As material spirals into a black hole, it heats up to millions of degrees. This hot material emits X-rays and other high-energy radiation. We can detect this radiation, redshifted into the infrared after billions of years of cosmic expansion. The specific patterns tell us not just that a black hole is there, but roughly how massive it is and how fast it's consuming material. This discovery will prompt a hunt for more such early black holes. If one exists at 570 million years post-Big Bang, there are probably others. Webb is still surveying the sky. Each deep field observation might reveal more of these mystery galaxies with unexpectedly massive black holes. Over the next few years, we'll build up a census of early universe black holes. That census will tell us how common they were, how they affected their environments, and whether our surprise at finding them reflects a real problem with our models or just incomplete observations. Late in 2025, the James Webb Space Telescope spotted something that shouldn't exist according to current galaxy evolution models. A massive spiral galaxy, complete with well-defined spiral arms and a structured disk, formed just 1.5 billion years after the Big Bang. They named it Alaknanda, after a river in India, and its very existence is forcing astronomers to reconsider how quickly galaxies can assemble themselves in the early universe. To understand why this is surprising, we need to talk about how galaxies form and evolve. Right after the Big Bang, the universe was a hot, dense soup of particles. As it expanded and cooled, matter clumped together under gravity. Small clumps merged into larger ones. Eventually, these became dense enough to start forming stars. The first galaxies were probably small, irregular clouds of stars without much structure. Over time, through mergers and internal evolution, these irregular galaxies developed into the structured spirals and ellipticals we see today. This process was thought to take time. Lots of time. Our Milky Way probably took several billion years to develop its current spiral structure. Other spirals we observe seem to have similar timescales. Spiral arms form when density waves move through the disk, concentrating stars and gas. This requires a stable, rotating disk, which itself requires the galaxy to have settled down from its chaotic formation process. Young galaxies should be messy. They're still merging with neighbors. Their orbits haven't settled. Their star formation is irregular. Structure and order come later, after billions of years of evolution. But Alaknanda throws a wrench in this timeline. It shows clear spiral structure in images captured by Webb. We're seeing it as it was 1.5 billion years after the Big Bang, which means the universe was less than 12 billion years younger than today. That might sound like a long time, but in galactic terms, it's early. It's like finding a mature oak tree just a few years after planting an acorn. The growth rate doesn't match expectations. The spiral arms are particularly puzzling. In modern spiral galaxies, these arms are regions where stars are currently forming. Gas and dust concentrate in the arms, creating conditions for star birth. The arms themselves aren't fixed structures. Stars move in and out of them as they orbit the galaxy's center. The arms are more like traffic jams on a highway. The cars move through, but the jam itself persists in roughly the same location. This kind of structure requires specific conditions. You need a rotating disk. You need density waves propagating through that disk. You need enough time for the waves to organize into coherent patterns. Alaknanda has all of this despite being formed so early. Its disk rotates. Its spiral arms show regions of active star formation. Its structure looks remarkably similar to modern spirals like our Milky Way, just smaller and younger. It's essentially a mature galaxy, appearing at a time when most galaxies should still be in their awkward, adolescent phase. This discovery connects to other findings from Webb's early observations. Since it started operating, Webb has consistently found more structure and organization in the early universe than expected. Large galaxies appeared earlier. Stars formed faster. Black holes grew bigger sooner. Each individual discovery is surprising, but together they paint a coherent picture. The early universe was simply more efficient at organizing itself than our models predicted. One possible explanation involves dark matter. We don't know what dark matter is, but we know it's there because of its gravitational effects. Dark matter doesn't interact with light, so we can't see it directly. But it interacts with regular matter through gravity. In fact, there's about 5 times more dark matter than regular matter in the universe. Dark matter provides the gravitational scaffolding that holds galaxies together. It's like the invisible framework inside a building. You don't see it, but it's supporting everything. Maybe dark matter behaved differently in the early universe, or maybe its distribution was different. If dark matter clumped more efficiently early on, it would create stronger gravitational wells. Regular matter would fall into these wells faster and organize into galaxies more quickly. This could explain why early galaxies like Alaknanda achieved structure sooner than expected. They had better gravitational organization from dark matter right from the start. In April of 2025, NASA's Lucy spacecraft made history by flying past an asteroid named Donald Johanson. This wasn't Lucy's main mission target, but it was a crucial test flight and an opportunity to study a main belt asteroid up close for the first time in this mission. What the probe saw has given scientists valuable insights into the early solar system and raised intriguing questions about asteroid evolution. First, let's talk about Lucy's mission. It's named after the famous human ancestor fossil, Lucy, discovered in Ethiopia in the 1970s. That fossil revolutionized our understanding of human evolution. NASA's Lucy spacecraft aims to do something similar for solar system evolution by studying the Trojan asteroids. These are asteroids that share Jupiter's orbit, clustering in 2 groups, one ahead of Jupiter and one behind it, trapped in gravitationally stable points. Think of them as Jupiter's cosmic entourage, following it around the Sun. The Trojan asteroids are interesting because they're primitive. They formed in the outer solar system and have been relatively undisturbed for billions of years. They're time capsules from the solar system's formation. By studying them, we can learn about the conditions and materials present when the planets were forming. Lucy will visit multiple Trojan asteroids over the next several years, gathering data on their composition, structure, and history. But before visiting the Trojans, Lucy needed to fly through the main asteroid belt, the region between Mars and Jupiter where millions of asteroids orbit the Sun. The mission designers decided to take advantage of this passage by doing a flyby of a main belt asteroid named Donald Johanson. This served as both an engineering test of Lucy's instruments and a scientific opportunity to study a main belt object in detail. Donald Johanson is named after Donald Johanson, the paleoanthropologist who discovered the Lucy fossil. The naming is fitting given the mission's theme. The asteroid itself is relatively small, just a few kilometers or miles across. Before Lucy's flyby, we knew almost nothing about it beyond its orbit. We had some vague ideas about its size and brightness from telescope observations, but no real details. Main belt asteroids are numerous, and most of them are essentially unknown. We've catalogued their orbits, but only a handful have been visited by spacecraft. Lucy approached Donald Johanson at a relative speed of about 5 kilometers or 3 miles per second. At that speed, the encounter was over in minutes. But Lucy's cameras and instruments captured hundreds of images and measurements as it flew past. What those images revealed was fascinating. Donald Johanson has a distinctive peanut shape. It's what astronomers call a contact binary or a close binary. This means it's either 2 objects barely touching each other or 1 object with a very deep waist in the middle. Imagine 2 balls of clay pressed together. That's roughly what Donald Johanson looks like. This shape tells us something about the asteroid's history. It either formed from 2 separate asteroids that collided gently and stuck together, or it's a single object that's been heavily modified by collisions and rotational effects. Many small asteroids have irregular shapes because they're too small for gravity to pull them into spheres. Earth is round because its gravity is strong enough to overcome the strength of rock, pulling everything into the most compact shape possible, which is a sphere. But asteroids are small. Their gravity is weak. Rock strength dominates over gravitational pull. So asteroids can have all sorts of weird shapes, elongated, irregular, peanut-shaped. Their shapes are determined by how they formed and what collisions they've experienced. The images also showed craters on Donald Johansson's surface. Craters form when smaller objects impact at high speed. Each crater represents a collision event. By counting craters and measuring their sizes, scientists can estimate how old a surface is. More craters mean older surface, because it's been sitting around getting hit for longer. Fewer craters mean younger surface, either because the object formed recently or because something erased the old craters, like volcanic activity or a major collision that resurfaced the asteroid. In early 2025, astronomers finally solved a long-standing mystery about one of the night sky's most famous stars. Betelgeuse, the bright red supergiant marking Orion's shoulder, has a companion star. For years, scientists suspected this might be the case, but confirmation came from combined observations by the James Webb Space Telescope and the International Gemini Observatory. They even gave the companion a nickname, Beetlebuddy. Betelgeuse is special for several reasons. It's one of the brightest stars in the night sky, easily visible to the naked eye. It's also huge. If you placed Betelgeuse where our Sun is, its surface would extend past Mars's orbit. We're talking about a star so large that you could fit more than 1 billion suns inside it. It's a red supergiant, which means it's in the late stages of its life. Betelgeuse started as a massive blue star, probably around 20 times the Sun's mass. It burned through its hydrogen fuel relatively quickly compared to smaller stars. Now it's fusing heavier elements in its core, while its outer layers have expanded and cooled, giving it that distinctive red color. Betelgeuse is also famous for being variable. Its brightness changes over time, sometimes significantly. Most of the time, these changes follow predictable patterns, cycles of dimming and brightening that last months or years. But occasionally, Betelgeuse does something unusual. In 2019 and 2020, it underwent what became known as the Great Dimming. It dropped to about 1/3 of its normal brightness, becoming noticeably fainter even to casual observers. This triggered speculation that Betelgeuse might be about to explode as a supernova. Such an explosion would be spectacular, visible even in daytime, brighter than the full moon. The Great Dimming turned out to be caused by a massive dust cloud that Betelgeuse ejected, which then blocked much of the star's light from our perspective. But the event raised questions about what triggers these dramatic mass ejections. Stars like Betelgeuse lose mass continuously through stellar winds, streams of particles flowing off the surface. But sometimes they eject huge amounts of material all at once. What causes this? And why does Betelgeuse's brightness vary irregularly even during normal times? The discovery of Beetlebuddy provides answers. The companion is a B-type star, meaning it's hot, blue-white, and massive. Initial estimates suggest it's between 10 and 15 solar masses, which makes it a heavyweight star in its own right, though tiny compared to Betelgeuse. Beetlebuddy orbits Betelgeuse every few centuries. The exact orbital period is still being determined, but it's probably somewhere between 200 and 500 years. On August 2nd, 2025, astronomers at the Pan-STARRS telescope in Hawaii discovered something unusual orbiting Earth. They designated it 2025 PN7, and follow-up observations revealed it's been co-orbiting our planet for at least 60 years, probably longer. This makes it one of Earth's longest-known quasi-satellites, and its stability over such a long period makes it an interesting object for both scientific study and potential future resource extraction. First, let's clarify what a quasi-satellite is, because it's not the same as a moon. Our moon is gravitationally bound to Earth. It orbits our planet following the rules of Newtonian mechanics. If you removed Earth, the moon would fly off into space. A quasi-satellite is different. It orbits the Sun, not Earth, but its orbit is configured in such a way that it appears to stay near Earth as both objects go around the Sun together. Think of two race cars on a track. They're not connected, but they're going at similar speeds and staying close to each other lap after lap. That's roughly what a quasi-satellite does. The object itself is roughly 200 meters, or about 650 feet across. That's about the size of 2 football fields laid end to end. It's not massive enough to have significant gravity of its own. You could probably jump off its surface and escape entirely if you jumped hard enough. But it's still a substantial chunk of rock, probably a remnant from the early solar system, captured into this unusual orbit through some combination of gravitational interactions over millions of years. In mid-2025, astronomers announced a discovery that sounds almost absurd. Saturn has 128 new moons. This brings Saturn's total to 274 known moons, more than any other planet in the solar system. Jupiter had held the record, but Saturn decisively reclaimed it. These new moons are tiny, irregular, and probably captured objects rather than moons that formed alongside Saturn. But they tell us a lot about the planet's history and the early solar system's dynamics. Before we dive into the details, let's establish what we mean by a moon. There's no official minimum size for a moon. If an object orbits a planet and is gravitationally bound to it, it's technically a moon. Saturn's rings are made of countless ice particles, each orbiting the planet, but we don't call each ice particle a moon because they're too small. The new discoveries are objects ranging from 1 to 10 kilometers, or about half a mile to 6 miles across. They're definitely moons by any reasonable definition, just very small ones. These moons are irregular, which is a technical term in planetary science. Irregular moons have orbits that are tilted, elliptical, and sometimes retrograde, meaning they orbit backward compared to the planet's rotation. This is different from regular moons like our moon, or Saturn's major moons like Titan and Enceladus. Regular moons have circular orbits aligned with the planet's equator, and they formed from the same disk of material that created the planet. Irregular moons formed elsewhere and were later captured by the planet's gravity. In November of 2025, radio galaxy surveys using the low-frequency array and other instruments delivered a stunning revelation. Our solar system is moving through the universe at over 1,000 kilometers, or 620 miles per second. That's 3 times faster than the standard model predicted. This discovery came from measuring our motion relative to the cosmic microwave background, the faint glow of radiation left over from the Big Bang that fills all of space. Think about what this means. Right now, as you're reading this, you're on Earth. Earth is orbiting the Sun at about 30 kilometers or 18 miles per second. The Sun is orbiting the center of the Milky Way at about 220 kilometers or 137 miles per second. The Milky Way is moving toward the Virgo cluster at about 600 kilometers or 370 miles per second. But when you add everything up and measure our total motion relative to the cosmic microwave background, the most universal reference frame we have, we're moving at over 1,000 kilometers or 620 miles per second. That's about 0.3% of the speed of light. The standard cosmological model, based on what we know about the universe's expansion and the distribution of matter, predicted we should be moving at about 370 kilometers or 230 miles per second. Finding that we're actually moving 3 times faster means something is wrong with our understanding. Either there's more matter pulling on us than we thought, or dark energy behaves differently than expected, or there are large-scale structures in the universe that we haven't fully accounted for. This measurement came from observing thousands of distant radio galaxies. These galaxies emit radio waves, and by measuring the frequency of those waves, astronomers can determine how fast we're moving relative to them. It's similar to how a police radar gun works. If you're moving toward a source of waves, the frequency appears higher. If you're moving away, it appears lower. This is called the Doppler effect. By observing radio galaxies in all directions and measuring the Doppler shifts, researchers could calculate our total velocity through space. As we look back at 2025, it's clear this was more than just another year of scientific progress. This was a year that fundamentally changed how we understand our place in the cosmos. We found visitors from other star systems carrying messages about distant worlds. We discovered hidden black holes lurking in nearby galaxies. We spotted galaxies and black holes in the early universe that shouldn't exist according to our theories. We found potential evidence of ancient life on Mars. We discovered new worlds that might harbor life today. And we learned that our motion through space is nothing like what we thought. Each of these discoveries would be significant on its own. Together they paint a picture of a universe that's more complex, more dynamic, and more surprising than we imagined. They remind us that for all our technological sophistication and accumulated knowledge, we're still explorers figuring out basic facts about the cosmos. We're still finding new neighbors in our solar system. We're still discovering fundamental things about how galaxies form. We're still learning how fast we're actually moving through space. The discoveries of 2025 also highlight the power of modern astronomy. We have space telescopes like Webb that can see back to the dawn of time. We have ground-based observatories that can track the motion of billions of stars. We have rovers on Mars collecting samples that might contain evidence of ancient life. We have spacecraft flying past asteroids we've never seen before. And we have computers that can process mountains of data, finding patterns that human eyes would never catch. But perhaps most importantly, 2025 showed us that the universe still has secrets. Despite centuries of scientific inquiry, despite all our instruments and theories, the cosmos can still surprise us. It can still show us things we didn't expect, things that challenge our understanding, things that force us to rethink our models and revise our textbooks. And that's not a failure of science. That's what makes science exciting. Every answer leads to new questions. Every discovery opens new avenues of exploration. The interstellar comet 3I Atlas reminded us that we're part of a galactic ecosystem exchanging material with other star systems. The silent black hole in the Large Magellanic Cloud showed us that much of the universe is hidden in darkness, waiting to be revealed by clever observations. The early universe discoveries from Webb demonstrated that cosmic history is more compressed than we thought, with structures forming faster and earlier than our models predicted. The potential biosignatures in the Chiava Falls rock brought us closer to answering one of humanity's oldest questions: are we alone? Even if those features turn out to be non-biological, the fact that we're seriously investigating Martian rocks for signs of ancient life shows how far we've come. We're not just speculating about extraterrestrial life anymore. We're collecting data, running experiments, ruling out alternative explanations. We're doing real science on one of the most profound questions we can ask. The discovery of GJ251c and other nearby potentially habitable worlds gives us targets for future study. These aren't just abstract concepts anymore. They're real places, orbiting real stars, places we might someday visit, or at least study in detail. Every new exoplanet discovery brings us closer to understanding how common habitable worlds are in the galaxy. And if habitable worlds are common, then life might be common too. The findings about our solar system's motion through space remind us that even basic facts about our cosmic environment can be wrong. We thought we knew how fast we were moving. We were off by a factor of 3. What else might we be wrong about? That uncertainty isn't disturbing. It's liberating. It means there's still so much to discover, so much to learn, so many surprises waiting in the data. 2025 was a year when technology, timing, and human curiosity aligned to produce an extraordinary harvest of discoveries. But it's not an endpoint. It's a beginning. Each discovery opens new lines of inquiry. The interstellar comet prompts plans for intercept missions. The early universe findings drive new observations with Webb. The Mars biosignatures accelerate sample return efforts. The nearby exoplanets become targets for atmospheric studies. The motion measurements spur revised cosmological models. In the decades to come, we'll look back at 2025 as a pivotal year, not because it answered all our questions, but because it asked new ones. Not because it solved the mysteries of the cosmos, but because it revealed mysteries we didn't know existed. That's how science progresses. Not in a straight line toward complete understanding, but in a branching network of questions and discoveries, each one leading to new territories to explore. The universe is vast, complex, and beautiful. It's full of wonders we're only beginning to comprehend. And if 2025 taught us anything, it's that no matter how much we learn, there's always more to discover. The cosmos will never stop surprising us, and that's exactly how it should be. There's also a connection to gravitational waves. When black holes merge, they send out ripples in space-time that we can detect as gravitational waves. Current detectors, like LIGO and Virgo, detect stellar mass black hole mergers. Future space-based detectors, like LISA, will detect supermassive black hole mergers. If the early universe was full of merging black holes building up into supermassive ones, there should be a background hum of gravitational waves from all these ancient mergers. Detecting that hum would provide independent confirmation of the merger scenario and tell us about the early universe's dynamics in a completely different way. In the broader context of 2025 discoveries, the CANU CSLRDZ 8.6 black hole stands out because it pushes our knowledge back to the earliest times. Most of the year's discoveries were about our solar system or relatively nearby parts of the galaxy. This one takes us to the edge of observable history, to a time when the universe was fundamentally different. It reminds us that our theories aren't complete. There are still surprises waiting in the data. And sometimes the biggest surprises come from places so distant we can barely see them, places that existed before most of the cosmic story had unfolded. Finding them and understanding them means rewriting the beginning chapters of the universe's history, adding details and revising plot points we thought we had figured out. There's also a connection to gravitational waves. When black holes merge, they send out ripples in space-time that we can detect as gravitational waves. Current detectors, like LIGO and Virgo, detect stellar mass black hole mergers. Future space-based detectors, like LISA, will detect supermassive black hole mergers. If the early universe was full of merging black holes building up into supermassive ones, there should be a background hum of gravitational waves from all these ancient mergers. Detecting that hum would provide independent confirmation of the merger scenario and tell us about the early universe's dynamics in a completely different way. In the broader context of 2025 discoveries, the CANU CSLRDZ 8.6 black hole stands out because it pushes our knowledge back to the earliest times. Most of the year's discoveries were about our solar system or relatively nearby parts of the galaxy. This one takes us to the edge of observable history, to a time when the universe was fundamentally different. It reminds us that our theories aren't complete. There are still surprises waiting in the data. And sometimes the biggest surprises come from places so distant we can barely see them, places that existed before most of the cosmic story had unfolded. Finding them and understanding them means rewriting the beginning chapters of the universe's history, adding details and revising plot points we thought we had figured out. The spiral arms are particularly puzzling because maintaining them requires ongoing processes. In a mature galaxy, like the Milky Way, spiral arms persist because density waves continuously compress gas and trigger star formation. But these waves themselves need time to develop and stabilize. They arise from gravitational interactions within the disk, particularly resonances with the galaxy's rotation. For Alaknanda to have stable spiral arms so early suggests either that these processes operated faster than we thought, or that the galaxy formed with some initial structure that made arm formation easier. Another intriguing aspect is the star formation rate in Alaknanda. Observations suggest it's forming stars vigorously, but not excessively. This is important because early galaxies often show extreme star formation rates, converting their gas into stars so rapidly that they burn through their fuel quickly. But Alaknanda seems to have found a sustainable rate, forming stars steadily while maintaining enough gas to continue the process. This requires a delicate balance of gas infall, star formation, and feedback from stellar winds and supernovae. Achieving this balance so early is another piece of the puzzle that doesn't fit our expectations. The discovery also raises questions about the role of environment. Was Alaknanda in a particularly dense region of the early universe where more material was available for galaxy building? Or was it relatively isolated, assembling its mass through steady accretion rather than dramatic mergers? Future observations might answer these questions by mapping the region around Alaknanda, looking for other galaxies or gas clouds that might have interacted with it during its formation. For theorists, Alaknanda represents a challenge and an opportunity. A challenge because it doesn't fit current models, forcing revisions to our understanding of galaxy formation. An opportunity because it provides a clear target for testing new ideas. If you propose a new mechanism for rapid galaxy assembly, it needs to explain Alaknanda. If your model predicts that early galaxies should be messy and irregular, you need to account for why this one is so structured. Good theories need to explain not just the average case, but also the outliers, the surprising examples that push the boundaries of what we expected. The companion's gravitational influence affects Betelgeuse in several ways. As the two stars orbit each other, their mutual gravity creates tidal effects. Think about how the moon's gravity creates tides on Earth, raising and lowering sea levels. Similar effects happen with stars, except instead of water, you're dealing with stellar plasma. These tidal effects can trigger instabilities in Betelgeuse's outer layers, causing it to eject material irregularly. This explains some of the brightness variations and could have contributed to the Great Dimming event. Binary star systems are actually quite common. More than half of stars form in binary or multiple star systems. Our Sun is unusual for being alone. Most stars have companions. But for many years, we didn't know if Betelgeuse was binary because the companion is so close to the bright supergiant that it gets lost in the glare. It's like trying to spot a candle next to a searchlight. The companion's light is overwhelmed by Betelgeuse's brightness. Webb and Gemini managed to detect Betelbuddy by using special techniques to block out Betelgeuse's light. Webb used its coronagraph, an instrument that creates an artificial eclipse by blocking the star's center. This is like using your hand to block the sun so you can see faint objects near it. With Betelgeuse's overwhelming light blocked, Betelbuddy became visible as a separate point of light orbiting nearby. Gemini provided ground-based confirmation using adaptive optics, a technology that corrects for atmospheric blurring in real time, creating images almost as sharp as space telescopes can achieve. The confirmation that Betelgeuse is binary has implications for understanding supernova explosions. When Betelgeuse eventually explodes, and it will eventually, though we don't know if that's tomorrow or 100,000 years from now, the presence of a companion might affect the explosion dynamics. In some binary systems, the companion star can strip material from the supergiant before it explodes, changing the explosion's properties. Or, the companion might survive the supernova, becoming a star, orbiting a neutron star, or black hole. Some types of supernovae are known to occur only in binary systems. Type Ia supernovae, which are used as standard candles for measuring cosmic distances, happen when a white dwarf in a binary system accretes material from its companion until it reaches a critical mass and explodes. Betelgeuse will produce a Type II supernova when its core runs out of fuel and collapses. But having a companion might affect the explosion's appearance and the remnant it leaves behind. In terms of composition, we don't know exactly what 2025 PN7 is made of yet. Spectroscopic observations are still being analyzed. But based on similar near-Earth asteroids, it's probably either a rocky S-type asteroid or a carbonaceous C-type. S-types are more common and are rich in silicate minerals and metals. C-types contain more carbon and water-bearing minerals. Both types are scientifically interesting and potentially valuable for future resource extraction. That's where this discovery gets particularly interesting from a practical standpoint. Asteroid mining has been a topic of discussion for years. The idea is that asteroids contain valuable resources, metals, water, and other materials that could be extracted and used in space rather than launching everything from Earth. Water is particularly valuable in space because you can split it into hydrogen and oxygen for rocket fuel. Having a source of water in space would make deep space missions more practical by allowing spacecraft to refuel. Near-Earth asteroids are the most accessible targets for potential mining operations. They're close, and reaching them requires relatively small amounts of fuel compared to going to the asteroid belt. But most near-Earth asteroids zip past Earth on elongated orbits. They're only nearby for brief periods before heading off to other parts of the solar system. 2025 PN7 is different. It stays near Earth all the time. It's always accessible. This makes it an ideal target for a mining mission if and when the technology and economics make such ventures practical. The 60-year stability is particularly important for mission planning. If you're going to invest in infrastructure to mine an asteroid, you want to know it's going to stick around. 2025 PN7's long-term presence near Earth makes it more attractive as a target. You could potentially park equipment there, return multiple times, and build up operations over years or decades without worrying that the asteroid will wander off. Many of these moons are probably in families, fragments of a single original object that broke up. When astronomers plot the orbits of Saturn's irregular moons, They cluster into groups with similar orbital parameters. Each cluster probably represents siblings, pieces of a parent body that's shattered. Over time, collisions and tidal effects can grind these fragments down further, creating even smaller pieces. It's possible that Saturn's rings were partly created by small, irregular moons that got too close and were torn apart by tidal forces, their fragments spreading into rings. Speaking of rings, Saturn's magnificent ring system might be related to these irregular moons. Current theories suggest Saturn's rings are relatively young, maybe only a few 100 million years old. They might have formed when a small moon wandered too close to Saturn and was destroyed by tidal forces. Or perhaps two moons collided and their fragments created the rings. The newly discovered irregular moons provide a population of potential ring-forming objects. Understanding how many there are, where they orbit, and how they interact helps us understand ring formation and evolution. One fascinating aspect of this discovery is the naming challenge. The International Astronomical Union is responsible for naming celestial objects, and they have conventions for Saturn's moon. Most are named after figures from Greek and Roman mythology, particularly titans and giants. But with 274 moons, we're running out of mythological figures. Some of these moons might end up with names from other mythologies or from literature, or perhaps they'll just keep their provisional designations, which are combinations of letters and numbers. It's a good problem to have, needing to name so many new worlds. The researchers used data from the Low Frequency Array, or LOFAR, a network of radio telescopes spread across Europe. They also incorporated data from other radio telescope arrays around the world. By observing thousands of distant radio galaxies and measuring the Doppler shifts in their emissions, they could determine our velocity relative to the cosmic microwave background with unprecedented precision. The cosmic microwave background is special because it represents the most universal reference frame we have. It's the afterglow of the Big Bang radiation that's been traveling through space for nearly 14 billion years. It fills the entire universe uniformly. If you measure your motion relative to the cosmic microwave background, you're measuring your absolute motion through space in the most fundamental sense possible. Previous measurements suggested we were moving at about 370 kilometers or 230 miles per second. This was consistent with what we knew about the local distribution of galaxies and dark matter. The Milky Way is part of the local group, which is moving toward the Virgo cluster. The Virgo cluster is part of a larger structure called the Virgo supercluster. All of these structures are moving relative to the cosmic microwave background. When you add up all these motions, you get our total velocity. But the new measurements show we're moving faster than that, much faster. This suggests there's additional motion we weren't accounting for. Perhaps there's a massive concentration of matter, a supercluster pulling on us from beyond the visible horizon. Or perhaps our understanding of dark energy needs revision. Dark energy is the mysterious force causing the universe's expansion to accelerate. If dark energy varies from place to place rather than being uniform, it could create large-scale flows of matter that produce these higher velocities. Another possibility involves cosmic voids. These are vast regions of space with very few galaxies, essentially empty bubbles in the cosmic structure. If we're near the edge of a large void, the asymmetry in matter distribution could create an effective push, accelerating us away from the void and toward regions with more matter. This would add to our velocity beyond what the simple model predicts. The implications of this discovery extend to cosmology more broadly. Cosmological models depend on understanding how matter moves through space on the largest scales. If our local motion is significantly different from what models predict, it suggests those models need refinement. This could affect our understanding of dark matter distribution, dark energy properties, or even the overall geometry and evolution of the universe. For practical space exploration, knowing our true velocity matters. When we plan missions to distant destinations, we need to account for our motion. If we're moving faster than we thought, it affects trajectory calculations, fuel requirements, and mission timelines. It's like planning a road trip, but being wrong about your starting speed. You'll miscalculate everything else. The discovery also connects to the anthropic principle and our understanding of why the universe appears the way it does. If large-scale velocities are higher than expected, it suggests the universe has more structure and more dynamic motion than our simplest models assume. This complexity might be necessary for galaxy formation, star formation, and ultimately the emergence of life. A universe with different large-scale dynamics might not have produced the conditions necessary for our existence. Looking at how this discovery was made reveals the power of modern radio astronomy. Radio telescopes can observe through dust and gas that blocks visible light. They can detect emissions from the most distant galaxies. And they can measure velocities with exquisite precision using the Doppler effect. The combination of multiple radio telescope arrays, advanced data processing, and sophisticated analysis techniques made this measurement possible. It's a reminder that astronomy continues to advance not just through bigger telescopes, but through better ways of using the instruments we have. The 2025 measurement of our solar system's motion will likely spark a flurry of follow-up studies. Researchers will re-examine other data sets, looking for additional evidence of high velocities or large-scale structure that might explain what we're seeing. They'll refine cosmological models, testing different scenarios to see which ones can reproduce the observations. And they'll plan new observations to measure our motion with even greater precision and look for the structures that might be causing it. This discovery reminds us that even the most basic facts about our cosmic environment can surprise us. We thought we knew where we were and how fast we were moving. We were significantly wrong about the latter. It's humbling, but also exciting. If we can be this wrong about something as fundamental as our velocity through space, what else might we discover? What other basic assumptions might turn out to need revision? In the end, the story of 2025 is a story about the joy of discovery. Every scientist who worked on these projects, from the engineers who built the telescopes to the graduate students who analyzed the data to the senior researchers who interpreted the results, they all share in the excitement of finding something new. They all contribute to humanity's growing understanding of the cosmos, and they all remind us that the universe is a place of endless wonder, always ready to surprise us if we're willing to look closely enough and think carefully enough about what we're seeing. Now I want to hear from you. Which of these 2025 discoveries do you think will have the biggest impact on humanity's future? Was it the interstellar comet teaching us about other star systems? The potential Mars biosignatures? The impossible early universe galaxies? Or maybe learning we're racing through space 3 times faster than we thought? Tell me in the comments which discovery blew your mind the most, and why.